All right, so I'm gonna go through a full example with one of the conics, not one of the conics, one of our quadric surfaces, and go through finding all the intercepts and all of the traces, and then trying to identify what kind of quadric surface it is. So we're going to find all of the intercepts in the traces, and then we're going to try to identify the following surface. X squared over 9 plus y squared over 4 minus z squared equals 1. Oh, I said squared, but I didn't write it. We are going to go through and we are going to find all of the intercepts, all of the traces, and then we're going to use the trace information to try to identify the name for this quadric surface. So I'm going to start with my intercepts. For x-intercept, we're only interested in the values where our surface crosses the x-axis. So we're not concerned about y values or z values, so you can set each of those equal to 0. So we're going to say y equals 0, z equals 0. Why is this not writing? There it goes. So if I set y and z both equal to 0, the only thing left in this equation is x squared over 9 equals 1. And now we want to solve for x. For x-intercepts, you're always going to be solving for x values. For y-intercepts, you're going to be solving for y values. And then all the other variables in the equation can equal 0. So if we solve this for x, we're going to multiply the 9 over. And then we're going to square root both sides. And be very careful, because when you use a square root in your equation to solve, to cancel out a squared, you also have to use plus or minus on the side with the number. So this surface actually has two x-intercepts at positive 3 and negative 3. Y-intercepts, we're going to let x equals 0, z equals 0. If we do that, we're left with y squared over 4 equals 1. And we're going to solve for y. So multiply the 4 over, square root both sides. We get y equals positive and negative 2. For the z-intercept, we're going to plug in x equals 0, y equals 0. What we get when we do that is negative z squared equals 1. This is not possible. In the real number system, this is not possible. If you try to solve this for z, we're going to have to divide over the negative. So we get z squared is negative 1. And then when you square root both sides, the square root of negative 1 is I. So technically, if we follow all the correct algebra, we get that our intercepts are positive and negative I, but we do not graph i's in the real number system. So the fact that this guy came out as a complex number means that there are no z-intercepts. We're only looking for real number answers. So far, so good? Yep. So those are all of our intercepts. The next thing I'm going to do is the traces. So let me copy this onto the next page. So we had x squared over 9 plus y squared over 4 minus z squared equals 1. So now let's go through all three of the traces. For the xy trace, we're going to let y or z equal 0, which means the z term in that equation just goes away. And what we're left with is x squared over 9 plus y squared over 4 equals 1. And this is where we have to look back at that list of conic sections and decide, based on the format of this equation, what kind of conic section it's going to create in the xy plane. So a couple of things to look for is both variables are being squared, so it's definitely not a parabola. Those squared variables are being added together, so it's definitely not a hyperbola. So we're down to just a circle or an ellipse. You guys think this is a circle or an ellipse? You gotta tell me why.
I think it's a circle because they're both squared and they're added together.
They're both squared and added together, so that it definitely still could be a circle. But it's not. It's an ellipse. Can anybody tell us why it's not a circle and it's an ellipse?
Because the radius isn't the same for both the x and the y.
Right. This number down here means that in the x direction, we're going to go 3 units left and right. But then this guy tells me I'm only going to go 2 units up and down. So I've got a different radius value in horizontally than I do vertically. What that's going to do is it's going to make it go out more left and right than it does up and down. So we get an ellipse. All right? So squared and added, it's definitely a circle and an ellipse, but the fact that they're divided by 2 different numbers makes it an ellipse. There really is no certain order you need to do these in. I'm going to do the xz trace next. For the xz trace, I don't see a y anywhere in that. That means I'm just going to let my y equal 0. So that entire y term is going to go away. And we're going to be left with x squared over 9 minus z squared equals 1. Both variables are being squared, so it's definitely not a parabola, but there is subtraction between. So that tells me right away I know what it is. Both squared with subtraction is a hyperbola. And remember, a hyperbola opens in the direction of whichever variable is not behind the minus sign. So here it's the x variable that's the positive term. So this is a hyperbola that opens in the x direction. And then for our last one, we've got to do the YZ trace. That last test problem is asking you what the equations for the traces are. So this is what they're asking you to find. This is the equation for the XZ trace. This is the equation for the XY trace. And then for the YZ trace, we're going to let x equal 0. So the whole x term is going to disappear, and what we're left with is y squared over 4 minus z squared equals 1. And what conic section is this?
Isn't it a hyperbola?
This one, yeah, this one's also a hyperbola. Both variables are squared, but they're being combined with subtraction. So that's enough information to know that it's got to be a hyperbola, and it's going to open in the direction of the positive, so y. Opens in the y direction. And this is the equation for that trace. Now, probably what the most the hardest part of all of this is to take all of that stuff and try to put it together to get a three-dimensional graph. I am not wonderful at graphing in 3 dimensions, and I don't expect you guys to be experts at it either. I'm not ever going to ask you to graph these by hand. In MyLabs Plus, these will always be multiple choice questions, so as long as you're able to find the traces and you know what they look like, you should be able to match it up with a graph if it's multiple choice. But I'm going to transfer all 3 of these traces onto the next page and then show you how I would come up with the graph for them. So we've got x squared over 9 plus y squared over 4 equals 1. That was our xy trace. And then we had x squared over 9 minus z squared equals 1 was our xz trace. And then y squared over 4 minus z squared equals 1 was our yz trace. And I think if I use some different colors, it might look a little nicer. All right, so the first one we said is an ellipse. So that is, if we slice this along the xy plane, which is the horizontal flat plane, we're going to see an ellipse that goes a little bit wider in the x direction than it does in the y direction. That's because the denominator for the x is a little bit bigger. So on the xy plane, I know I'm going out 3 units in the x direction because those were our intercepts, and I'm going 2 units in the y direction because we also found those as our intercepts. And if we try to connect them, it's not going to look beautiful just because of the way that we have to orient our three-dimensional space, but imagine that blue ellipse being perfectly horizontal and flat. In the XZ trace is a vertical trace that slices into the screen. It comes out at us the way the x-axis does, and then it goes into the screen following the negative x-axis. And we have an ellipse, we've got hyperbolas opening in the x direction. So what that means is back here, I've got a hyperbola that opens in the negative x direction, and then up here, I've got a hyperbola, well, it's supposed to connect, that opens in the positive x direction. So I've got like my 2 parabolas opening away from each other. One opening in the positive x direction, one opening in the negative x direction. And then we also have a hyperbola in the YZ plane. The YZ plane is your computer screen. That flat, vertical, Z is up and down, Y is left and right. That is our YZ plane, and we know we also have a hyperbola there, but this one opens in the positive and negative Y directions. So we're going to go to our y-intercepts and draw another set of hyperbolas. And these guys, yeah, they look really, really weird. One thing that hopefully, as we practice these more and more, we will understand is that this ellipse that we're seeing in the xy plane, remember, we could also slice parallel to z equals 0. So if we were to slice up higher, we would just get a bigger ellipse. If we would slice down lower, we would get an even bigger ellipse. If we go up even higher, it's even bigger. If we go down even lower, it's even bigger. So what we have here is kind of like this flared cylinder. And there are structures actually locally that are built like this, and they're built like this for a reason. Has anybody seen a structure built in this shape before?
Looks like a reactor.
It is. It looks exactly like the Sharon Harris nuclear plant, and there's a reason for that. And I don't know the reason. I should find it out. That would be a much more interesting lecture. But
Probably because there's so much mass from the concrete, they won't fall on top of each other.
yeah, definitely the way that this is flared, it's flared at a rate where it's going out slow enough that the concrete is strong enough underneath to still hold it. I have a feeling though, and this is just me guessing, that as stuff happens down here, when the radius of any sort of tube starts to decrease, whatever is flowing through it inside speeds up. So it's possible that this is shaped this way to kind of induce the exit of the materials out the top. That's my guess to help it along. So the traces here are an ellipse and some hyperbolas. This guy has a weird name. It doesn't have ellipse in it anywhere, but it does have hyperbola in there, and this is called a hyperboloid of one sheet. The most important part of understanding this kind of shape is the fact that it's made of hyperbolas. We have two different hyperbolas, so that's why it's a hyperboloid, but it's only those three different traces come together to make one solid object. So that's why it's a hyperboloid of one sheet. There is a hyperboloid of two sheets that has hyperboloids as traces, but when you graph it, it makes two separate objects. So that one's called a hyperboloid of two sheets. So the fact that it's hyperbolas and it makes one solid object, it's a hyperboloid of one sheet. And we found the intercepts, we found the traces, the equations for the traces, and the name for the conic sections of the traces, and tried to put it all together. Anybody have questions so far? I'm going to do another one. And I'm not going to do as much of this as this one. I'm going to ask you guys lots of questions, okay? So feel free to jump in and answer questions. Also, do not worry about being wrong. There's absolutely nothing the matter with being wrong. So I don't want you to sit there and be quiet just because you're like, I don't want people to think I don't know this or it's wrong. We're all learning this. Not me. You guys are all learning this together for the first time. So please do not worry about answering questions and being wrong. That's how I know that I need to explain it differently or explain it better, because something's not clicking. So just my 2 cents about answering questions. So we're going to find the intercepts and traces again. And we want to identify what this surface is. And for this one, we are going to have y plus x squared over 4 plus z squared equals 0. This guy's going to be fun. I have no clue what it is right now. Not until I find my traces. I have no idea. But we're going to start with our intercepts. For the x-intercept, you're going to let y and z equal 0. All we're left with then is our x term. And if x squared divided by 4 equals 0, that means x has to equal 0. That's the only option. And this is going to actually be true of all of them. the y-intercept, you're going to let x and z equal 0, and what we're left with is just y equals 0. And then for our z-intercept, if you let x and y equal 0, you're left with z squared equals 0, which means z equals 0. So all of the intercepts are 0. And the point where all of the values equal 0 simultaneously is called the origin. So all of these guys come together right there at the origin, and that's the only place this surface ever touches our axes. So just having our intercepts is not very helpful. All we get is a single point. So let's move on to our traces. XY trace. What will the equation look for the XY trace? So you're going to go back to the original here, and you're going to let z equal 0, which means z is going to go away. Is somebody talking? I thought I heard something in the background.
Yeah, he was talking, but we can't hear him.
Okay.
Sorry, I was laying back in my chair.
It's okay.
I said the trace should be y plus x squared over 4 is equal to 0.
Yeah. The z piece goes away, and that's what we've got. It's kind of hard to identify the conic section in this format, but you can without having to do any rearranging, because one of our variables is not squared. So automatically I know what this is. There's only one conic section where all of the variables are not squared, and what is that? It's a parabola. We're used to seeing parabolas as like a y equals equation, so we can put it in that format if we take that x squared over 4 term and subtract it over. And that's actually helpful in deciding the shape of our graph, because I can see that this is a parabola that opens in the y direction, and because my coefficient is negative, it opens in the negative y direction. So we've got a parabola here that opens in the negative y direction. So positive y is this way, negative y is this way. The xz trace is the flat one, the horizontal trace. So I'm going to go ahead and add this right now. In my xy trace, I've got a flat parabola here in the xy plane that opens in the negative y direction. So far. Hopefully our xz and our yz trace will help us to figure this out a little bit better. So I've got to go to the next page to do the other two. So far we know that they all come together at the origin, and that's the one intercept. It never, ever, ever crosses any other axes. And we also know that if we slice this thing horizontally, we're going to see a parabola opening in the negative y direction on the xy plane. All right, let's go on to our next one. I'm going to do the xz trace next. So I'm going to let y equal 0. Then we get x squared over 4 plus z squared equals 0. And this one's kind of tricky. The only time that you are allowed to add two squared values together and get 0 is if one of them, or if both of them are 0. That's the only way this is possible. Because adding makes numbers bigger. So if I were to add something to the x, it should go higher than 0. If I was to add something to the z, it should go higher than 0. Because remember, no matter what you square, the answer is always positive. The only time this is ever going to happen is at the point 0, 0. And we already know about that point. So this is a good example of where it is helpful to maybe not plug in y equals 0, but plug in some sort of constant for y. So this is what we get when y equals 0. Not really helpful. Let's plug in a different y value. What if we plug in like y equals 5? Then this equation is going to be 5 plus x squared over 4 plus z squared equals 0. And just after a little bit of rearranging, I've got the sum of two squared values is equal to a negative. Any positive y value that I plug in here is going to give me the sum of two squares as a negative. That means that there are no positive y values on this graph. This is not possible. In order for this to work, we would have to plug in a negative value for y and then add it over to the right-hand side. So I'm going to do one more of these. Let's say y is negative 4. Then my equation is going to say negative 4 plus x squared over 4 plus z squared equals 0. And I can take this guy and add him over, and that makes a whole lot more sense when I'm trying to identify a conic section. So I've got both variables squared and added together. That's going to cut our options down in half. If they're squared and added, it has to be a circle or an ellipse. So what do you guys think? Is this one a circle or an ellipse? And why do you think that?
It's an ellipse because the radiuses are different.
Perfect. Yep. Our x has got a denominator and our z does not. Even if we were to set this equal to 1 by dividing everything by 4, they would still have different denominators. So what that means is we've got an ellipse in the xz trace, but it's only there on the negative y side. So we've got these ellipses over here on the negative y side that come together to a tiny little point at the origin. And then the YZ trace, I can pretty much tell what this is now, just because I have experience with it. But I want to go ahead and throw in the YZ trace here on the same page if I can squeeze it. For YZ, we're going to have y plus z squared equals 0. We've got one linear variable, one squared variable. It has to be a parabola. And actually, let me write this down here. So with parabolas, we usually like them solved for the linear variable because then we can look at the coefficient and decide if it's opening in the positive or negative y direction. So this is a parabola that opens in the negative y direction because of that negative coefficient. So my YZ trace, which is the board, which is your computer screen, we've got another parabola opening in the negative direction. So this. So what that does, it just rounds out the other kind of sides of this thing. What we have is, it's like a bowl laying on its side, made out of parabolas. So what this is called, because we have an ellipse and some parabolas for our traces, this guy is called an elliptic paraboloid. Elliptic paraboloid. So there is a lot packed into these problems, and it requires you to really remember a lot of algebra, a lot of graphing techniques, a lot of conic sections. It's very involved, which is why there's only one question, because it has so many parts to it as well on the test. All right, questions so far? all of our quadric surfaces, we can do the same thing with. Find all the intercepts, try to identify all the traces, and just see how all of those pieces kind of fit together to make our three-dimensional shape. All right. Hey, Larden. Questions?
Good now.
Okay, wonderful. We've got about 8 minutes left in this this little session. Is there anything you guys want to talk about real quick for 8 minutes? All right, I'm going to bore you then, and I'm going to do one more thing really quick from 13.6. This one's much easier and much shorter, but I have not talked to you yet about cylinders. There's no test question on cylinders. There might be a couple of homework questions, but there's no test questions about it. But it's really important, mostly because of one algebra thing I want to point out that it's possible your algebra teacher never talked about. I'm going to switch back to my white screen real quick and show you how you can very, very quickly and very easily identify a three-dimensional cylinder. And it's going to cut us off at 2:40. I will, anybody who wants to come back at 3, I'm going to start talking about stuff from chapter 14. And I've already got that Zoom meeting set up. As soon as this one cuts us off, I'll send you the link to the next one for anybody who wants to come back at 3, okay? And at 3, I'm going to do some chapter 14 stuff. All right, so let me show you real quick cylinders. I'm going to open back up my, if I can find stuff. Where is it? I'm going to stop my video, and I'm going to share my screen. All right, so the reason I want to talk about cylinders is because it's not the same cylinders that you probably learned about when you first learned about three-dimensional shapes back in elementary school or middle school. So in Calculus 3 and beyond, cylinders actually have a much more general definition. A cylinder in 3 dimensions is this is a 3-dimensional surface where a 2-dimensional curve gets repeated infinitely in the direction of the missing variable. So cylinders in 3-dimensional space are not going to look like 3-dimensional equations. They're going to look like 2-dimensional equations, like back from algebra and calculus class. You most likely learned a cylinder looks like a can. And that is true. A can is a cylinder. The reason it still follows the rules that we're going to talk about is that we have one 2-dimensional shape here. We've got a circle, and that circle gets repeated forever along the z-axis, up and down. That is the general definition for a cylinder. It does not have to be a circle that we use. We can use any 2-dimensional shape we want to create a cylinder. So the technical name for this guy is a right circular cylinder. It's a cylinder because it's one 2-dimensional curve that gets repeated forever in a third direction. Circular refers to the 2-dimensional shape that we're using to create the object. And the right means this thing is standing perfectly upright at 90 degrees. It's possible that we could have it slanted. That one would also be fine. That's also a cylinder, but it's not a right circular cylinder. It's just a circular cylinder. So let me show you one quick equation. We've got just a couple minutes left. We're going to sketch a graph of the three-dimensional surface. Almost always the directions for these problems will very specifically tell you that these are three-dimensional, and I spelled that wrong. They have to tell you in the directions these are three-dimensional surfaces, because when you first look at the equation, they are they've only got two variables. So let's I'm gonna do z equals y squared. Now I have said this is, I feel like I still spelt that wrong. You guys, I'm like brain dead right now. I'm sure that's spelled wrong. I think the S was right. And I don't know, I'm leading it. Sorry. Even though we only see two variables, they tell us in the directions this is three-dimensional. So what that means is that this guy, just as a two-dimensional curve, we know it's a parabola because one variable is linear and one is squared. It's a parabola in the YZ plane, and it opens in the direction of the linear variable. So it's a parabola that opens in the positive Z direction. So I'm gonna draw this two-dimensional curve in three-dimensional space. This is just a two-dimensional parabola in the YZ plane that opens in the positive Z direction. So it looks like this. Because the X is missing, what that means is this shape gets repeated forever along the x-axis. So I don't have to put it right there at x equals 0. I can also put it out here at x equals 4. And I can also put it back here at x equals -5. And when you connect these guys, what you get is a half pipe. You see that? The variable that's missing is the variable that we're allowed to repeat that curve forever in that direction. Because really all an equation is a restriction. And if an equation is missing a variable, that means there are no restrictions on that variable. So that's why we can take this one curve and repeat it forever in the x direction. And this would be called a parabolic cylinder. And I'm about to get cut off. So if anybody wants to come back and hear some of chapter 14, then I'll see you back at 3 o'clock. And I did record this one. That way I can post it. And I'll record the next one as well. All right. See y'all soon.